Now let's look at an application that involves the acceleration components in both the tangential and normal directions. So we have the functions r of t, which is t, 2t, and 3t, and capital R of t, which is t squared, 2t squared, and 3t squared, are different parameterizations of the same line. Why is that the case? Then find the velocity, acceleration, and tangential and normal components of acceleration for both parameterizations and use your results to draw a conclusion about motion along the line. All right, so let's start off with why it is the case that they are the same parameterizations. So this is just a little review here of parameterizing. So R of t, which is t, 2t, and 3t, right? If I made it R of t squared, that would be t squared, 2t squared, and 3t squared, which is what capital R of t is. So recall, there are infinitely many possible parameterizations for the same curve. Let's look at this in Desmos, actually. So if I have my Desmos graph right here, I'm actually looking at the function y equals x cubed, but the idea still holds even if it's in 3 dimensions, which is, if you want to look at y equals x cubed, I started with parameterization where x was equal to t. So it'd be t cubed. That's one parameterization. But I could also have used 2t, right? They cover the same curve, right? So there's the green dot coming through. That's the second parameterization. So they both work, they both cover the curve, but they go through it at different rates, different speeds, different times, one might say, for the t variable. Or I could use t over 2, which would go through half as fast because it's slower. Or t cubed, which will shoot through very quickly. Give t cubed a chance. There it is. That's the black one. So you can see that you can have infinitely many different parameterizations. I did 4 here, and that would still create that same curve. So if I turn off the curve, those colored dots are still following that path, right? Okay, so the fact that if I take my particular problem and I substitute t squared into this function and I get that function, that means that they are different parameterizations of the same line or curve, right? So they are the same line. If you graph them in 3 space. All right, so we've answered that question. Now let's find the velocity, acceleration, and tangential and normal components of acceleration for both parameterizations. Oh, so something small then. All right, so let's look at A for a second. I'm just going to label this A just to make my life easier. Okay, so for A, so we kind of took care of the Y right there. So for A, I want the velocity function. Well, velocity would be 1, 2, and 3. And then I want the acceleration function, or acceleration, well, it is a function, it's a vector valued function, but the acceleration vector, which would be, well, the derivative of this, right? So it's v prime. But v prime, if you look at v, they're all constants. So their derivative is 0, 0, and 0. Okay. Well, that means that there's, let's think about this, constant velocity, right? Because 1, 2, and 3 are all constants. And that yields no acceleration. Or if you like, 0 acceleration. And that means if there's no acceleration, then that means that the component in the tangential direction and the component in the normal direction would both be 0. Right? Because if you take the dot product, I mean, if you think about the definition of the tangential components of acceleration, one involves the dot product of the acceleration vector, but that's a 0 vector. One involves the cross product, but it's a zero vector. So the dot product with a zero vector is 0, and the cross product with a zero vector is still 0. So it's going to be 0, which is why these are both 0. All right, now let's look at B, which is going to be this parameterization right there. Okay, so V of t is equal to the derivative of R of t. So V of t is equal to, let me pull this out right here. V of t will be, and this is really for capital R. These ones over here were for little r, just to kind of make sure that they're clear, right? So for capital R, V of t is the derivative of capital R of t, which would be 2t, 4t, and 6t. All right. Now, what about the acceleration vector? The acceleration vector, I don't want to use orange, sorry, purple. Okay, so the acceleration vector for capital R would be equal to the derivative of the velocity vector for capital R, which would be 2, 4, and 6. So the derivative of that one. All right, then the tangential component, a sub t, would be equal to v dot a, right, the velocity dot product with the acceleration vector over the speed. As a matter of fact, let's go right over here real quickly and find speed. The magnitude, oh, sorry, it was from this one, not from that one. Sorry about that. The magnitude of your velocity vector, which is your speed, is the square root of 2t squared plus 4t squared plus 6t squared. Oops, got to make my square root go farther. So that would be the square root of 4t squared plus 16t squared plus 36t squared, which would be the square root of 56t squared, which is t square root of 56. So this is speed right here. Okay, why did I do that? Well, it just makes things a little easier over here, because now I want the dot product, but I want to divide it by that t square root of 56. And the dot product would be the velocity vector, which is 2t, 4t, 6t, dot product with that acceleration vector of 2, 4, 6. That would yield an accelerational component of, well, let's see, 2 times 2 is 4, 4 times 4 is 16, and 6 times 6 is 56. So this would be 56t over t times the square root of 56. Of course, the t's divide away, so that leaves you, I ran out of space, that leaves you 56 divided by the square root of 56, which if you rationalize by multiplying by the square root of 56 over itself, you end up with 56 square root of 56 over 56, which is the square root of 56. Just a little recap on rationalizing there really quickly in case you missed it. So over here, the t's are dividing away to 1, so those go. All right, so there we go. That is 2 square root of 14. That is a sub t. And you'll notice it's constant. So your acceleration in the tangential direction is constant, in the t direction, right? In with the tangent. Okay, so now what about the other piece, the normal piece? So a sub n. To do a sub n, I'm going to need the cross product of the v vector and the a vector. So I mean velocity cross product with my acceleration. So I'm just going to take the cross product now and get it over with. So velocity is 2t, 4t, 6t. And then acceleration is 2, 4, 6. Okay, so my cross product would be 24I, 12t, oops, ran away there, 12tj, and 8tk minus, and then reverse it, 8tk, let's see, 24ti, and then 12tj, 6 times 2, which would be, well, let's think about it, 24, 12, oh, it was 24t, oops, my fault, 24ti, there we go, 24t, 12t, and 8t. Take away 24t, 12t, 8t. Uh-oh. That's the zero vector. Your cross product is zero vector. Therefore, an is equal to, let me just write down the formula. It's the cross product of velocity and acceleration divided by the speed. That is equal to the magnitude of the zero vector. Here, if you want to see it, 0 squared plus 0 squared plus 0 squared. I don't know why I'm bothering, but there you go. Divided by the square root of 56 times t, which we all know is 0. That's a constant. It's a scalar, not a vector. I was just thinking. So moving along a straight line, with no curve or bend to it will always have a normal component to the acceleration equal to 0. It has to, because it has no curve. So we're looking at a line. As you move along a line, there's no curve or arch to it. Therefore, you can't have a normal component of the acceleration, because that's based on the curvature of the path that you're following. So if your path has no curve, then there's no a sub n. There's no acceleration in the normal direction. There can be acceleration in the tangential direction, because that's how fast you're moving in the line. Well, not how fast, but it's how fast you're accelerating as you move along the line. This is acceleration along the line. I can't spell the word acceleration. I'm running out of paper here. Acceleration in the direction of the line. Or path, if you like.